Welcome. In this lecture, we are going to talk about current loop stability in digital current mode control, and then what is the cause of current loop instability and how to stabilize the current loop using ramp compensation with experimental result. So, we will first show the sub-harmonic instability in mixed signal current mode control, where we want to keep a fixed current reference, and we will show some experimental case studies. Then we will also show ramp compensation for current loop stabilization, and what are the limitation of ramp compensation while duty ratio operation, and what is the impact of current loop instability in power spectral density as well as the RMS parameter. So, in mixed signal current mode control, we are all familiar with this current mode control architecture, and we have explained multiple times. So, I am not going to explain again. And if you recall, I think we have discussed in week 5, where we have considered the current loop stability using discrete time model. So, I just want to summarize. If you write the full equation of ILN plus 1, which is this current, in terms of ILN and duty ratio, then if you get the part of dynamics, that means you can get only the part of dynamics. The ILN perturbation will be a function of IL perturbation and also a function of IREF perturbation. Okay. But if we do not perturb the reference current, that means we are talking about the fixed reference current, where only inner loop is closed and we are using a fixed current reference, then IREF perturbation is 0, then only this term will remain. And in order to stabilize this thing, we know that this particular term, magnitude of this particular term must be smaller than unity, so that the eigenvalue should be inside the unit circle, and this is exactly what that eigenvalue. And if you further summarize, we know that for d less than 0.5 the current loop is will be stable. But if we go beyond d greater than 0.5, then the current loop will be unstable, and we are going to consider experimental hardware case study, where we are considering our traditional 1.8 volt inductor, 1.8 microhenry inductor, 200 microfarad capacitor, and here we are not closing the outer loop. So, this output voltage can vary. We are allowed to vary because regulation may not be perfectly achievable, because we are only giving a fixed current difference. But we are operating at 200 kilohertz, and load resistance we have considered that there are two resistance, but for this particular case we have turned on the switch resistance. So, the R effective we are considering 0.32. That means this is considering both the resistance in parallel, and the controller we are not using any controller. So, I will say instead of controller it is the hardware details, where we are using a reference peak current. That means we are applying a peak current which is 3.4 ampere, and we are actually comparing the inductor current with this peak current. That means this is the inductor current we are comparing. So, 3.4 ampere is the current difference, but that is the physical current difference, but actual implementation, because there will be a current loop gain and etc. So, then the number will vary, but when I will show the experimental result, it will show 3.4 ampere. And we all know that current sensor also have a gain, because it is a current sense resistance followed by amplifier. We also consider DAC resolution 12 bit, because we are sending the data through DAC, and the controller clock is 200 megahertz. Feedback voltage gain is 0.27, but we are not closing the outer loop, so you do not have to care. Now, I am showing a first experimental case study, where we are setting the input voltage 2.5 volt, load resistance is 0.32 that I have told, peak current reference is 3.4 ampere, and switching frequency is 200 kilohertz. And if you see the experimental result, and you see this division is 1 ampere for the current, and the voltage if you see 1, 2, 3, 4, 5, it is almost 1 volt, because we are setting the current reference such that the output voltage is reaching 1 volt, but we have not closed the loop. And you can see the peak current difference is coming to be roughly around 3.4 ampere. That means if I use a different color, so this is 3.4 ampere. And another interesting point is that here it is more or less stable. That is why I have shown the FFT. This is the FFT of inductor current, and you see this FFT is this particular division is 250 kilohertz. That means here we are getting a peak, which this peak is at 200 kilohertz, and that is our switching frequency. So, we are getting a sharp peak at 200 kilohertz and then harmonics with respect to that fundamental component. Because it is stable, so you can see power spectral density, that is kind. Another interesting point, we should remember what is the current ripple. So, the current ripple, if you consider, it is coming just below, it's around 1.8 to 3.6. So, roughly I think it is around 1.8 ampere is the current ripple, that is our current ripple. Roughly it may be slightly higher, I think it will be almost like 1.8 to roughly around 2 ampere. It is not exactly correct, but maybe around 1.8 or so. Okay, let us consider it is in 1.8 because we have not regulated the voltage. Now, what we have done, we have decreased the input voltage. So, earlier the case 1 was 2.5 volt, now we have reduced to 2 point, this is V in 2, this is V in 2. What will happen? You see, slowly the sub-harmonic has started, because you see the in between this peak it is reduced, because if you take this is 0.1, this is another point, this is another point. So, 0.1, 0.3 they are sort of repeating, but 0.2, 0.4 sort of repeating. So, slowly sub-harmonic oscillation just started, and this is also clear evident from this peak which is at 100 kilohertz, because we are talking about sub-harmonic. So, sub-harmonic means this peak is at 100 kilohertz and the switching frequency peak as 200 kilohertz. So, that means we can see the power spectral density is sub-harmonic, that is why you sometimes call sub-harmonic instability, because it is half of the switching frequency. Now, what will happen, and here the ripple impact is not fully visible. Now, we are further decreasing to 2.2, just increase by 50 millivolt, decrease by 50 millivolt, and you will see a drastic change in the current parameter, and now this peak has gone up. This is at 100 kilohertz. So, that means you have a dominant effect of sub-harmonic component, and that is also obvious in the ripple parameter, because it will increase. And you can see this current peak to peak current ripple, that means if I say IL peak to peak, how much will be that? So, this division will be almost 1, 2. So, it is crossing, it is I would say more than 2 ampere. So, that means the current peak to peak is higher than the current ripple that we have seen. Next part, if we further reduce to 2 volt, now the effect become more prominent. So, that means you see now the sub-harmonic component is dominating over the fundamental component. That means you have a clear evidence, and the ripple current has significantly, peak to peak has significantly decreased. So, then if we further decrease, then you will see the switching frequency become half, is like become half, because this to this it is 20 microsecond, you can see this is 20 microsecond. So, this will be 10 microsecond, but we have 5 microsecond 200 kilohertz switching frequency, and this is because of nonlinear phenomena, and you can see that output voltage also goes down, because your peak current is fixed. So, this guy is going down, so the average will be going down, as a result your average voltage. So, you need to anticipate, this can be regulated by an integral control, but this instability can cause a large ripple current as well as voltage. So, this impact of sub-harmonic, if you say 2.5 and 2.6, it is clearly visible in terms of power spectral density. The RMS current we saw, there will be a obvious increase in the RMS current because of the instability, and ripple parameter is also increasing peak to peak. And if you take the power spectral density, you can see the sub-harmonic component become more dominant compared to this case. So, this is more dominant sub-harmonic content, and which is not desirable. Now, we know about RAM compensation. If you add the RAM compensation, then the duty ratio expression will get changed, and if you get the part of dynamics for fixed current reference, it can be shown that the current loop will be stable if the compensating ramp is greater than this, but we have to make sure if the duty ratio less than 0.5, then by this calculation MC become negative, but we are not going to use ramp when. So, that means we will not use ramp. So, MC not needed in that case, but when you close the loop, in fact we may need this MC even at slightly lower duty ratio because of the closed loop effect. Then if you add the ramp, then this was before adding ramp at 2.2 input voltage. After adding ramp, now it becomes stable. So, what we are doing, because we have a fixed current reference, now through the DAC we are generating also a ramp with this kind of thing. So, from digitally inside, and then inductor current is getting compared with this, Since we are using a very low ramp, that means the peak has not changed drastically. It should have reduced from 3.4, but the reduction is very small because the ramp is very small. And because of the using of small ramp, even at 2 volt where it was totally unstable, here also it is unstable, but it has improved, but it is not purely stable. So, what we have to do? We have to increase the ramp slope. That means, for stabilizing the current loop when the duty ratio varies widely, for large duty ratio operation, your ramp slope has to be increased, and this can be computed from this slope. But if we use a large ramp throughout, then what will happen? In fact, it is well known fact that you can, because the same design, if you add more and more ramp, so the benefit of current mode control is lost, because by virtue of closing the current loop, we want to control, we want to actually replace, or you want to mimic the inductor to be a control current source. But when the ramp compensator is added, then the 2 pole, because when there is a single pole approximation in current mode control, the capacitor pole and inductor poles are separated, the inductor pole goes far away, but when you add more ramp, then these 2 poles again start coming close to each other, and if you add more ramp, then it will slowly become voltage mode control. So, all the benefit of current mode control will be lost. So, that means a very high ramp compensation may not be desirable. So, that means the limitation is that high ramp compensation may not be desirable, because it will affect, it may not be desirable, because what will happen for even for nominal duty ratio or stable operation, it will not behave like a current mode control, because you are adding ramp. So, you are losing the benefit of the single pole approximation. So, your compensator design has to be redesigned. That means, your PI controller may not be enough. So, you may have to configure PID controller, and also it may affect, if you consider the PI controller, it may affect your phase margin, and that is why you may have to reduce the crossover frequency. So, your overall controller has to be slow down. You have to slow down the controller. So, that means the high ramp compensation may not be desirable. But in digital control, so this is for throughout the fix, but you can also consider dynamic ramp compensation. How? Because you know this ramp, we are using the digital platform, that means the current reference minus your this ramp, right? This is all under, and this is now going to the DAC, and this is actually compared in the, so this is your peak voltage and this is your sense current, and we have this current loop sensor gain IL. So, what I am saying, since it is inside the digital platform, so you can always play with the ramp slope inside the digital platform. So, you can do a dynamic ramp compensation, or you can actually disable this ramp during transient, enable this ramp during steady state for stabilization. So, all this play around, I mean you can play around this control strategy we have to be very careful about this dynamic mechanism, because you need to identify suitable transient and steady state condition, or based on your duty ratio, if you keep on watching the duty ratio, you can simply extend the ramp and keep it throughout during transient and steady state. So, all these possibilities exist in digital control, but now we want to show a live demonstration of digitally current mode control fixed frequency with fixed current difference with and without ramp using hardware prototype. Now, we are going to consider the mixed signal current mode control, and we want to see the current loop stability where we have used a fixed current reference. So, first I am running this Verilog code. Actually, this is now we can compile this code. There are steps, and I think all the steps we have discussed in the previous lecture. So, I am just going to browse through those steps very quickly, and this is the code where we are actually generating the reference current, and we have the provision for ramp compensation. There is an external switch by which we can add the compensating ramp. So, now once we run this code, then once the program file is generated, then what we have to do, we have to select this particular file and this bin file, then we need to program it. So, it will take some time, and once this programming file is dumped into the FPGA, into the flash memory, and then we will be ready for running the actual hardware. So, this is the step where our Verilog files actually synthesize, then it generates the implementation detail for the FPGA prototyping, and it also generates the .bin file. Now, this bin file we are using another interface, and we have demonstrated that MIMA's FPGA configuration for this particular FPGA, which is down, and now this program is dumping into the FPGA. So, we will take another maybe less than a minute to complete this dumping process. Now, the computer will be out of the real time loop, and we are going to demonstrate the current mode control. So, we are almost in the final stage of our demonstration now. So, this shows it is done. Now, we are coming to the actual demonstration. So, this is the power supply where we have the first channel, this the second one is for powering different IC, ADC, DAC and all, and the first channel is our actual power input. So, if you turn on this power input, this is the scenario. We have set 2.5 volt is the input, and as we have discussed in the lecture, we have used a fixed current difference which is at 3.4 ampere. Now, in this 3.4 ampere, actually this is the output voltage, and we are going to see stability. So, in this condition, we are turning on the FFT algorithm, and this FFT we are taking at channel 4, and we are showing this FFT. We want to take this FFT here first, and then we want to consider 250 kilohertz range. Now, we are taking this FPGA screen. So, this is a 0 frequency coming. So, 0 frequency is here now. So, now we have placed the 0 frequency here. So, you can see there is a spectral peak at 200 kilohertz, because this length is 250 kilohertz and this one is 200 kilohertz. So, that is our switching frequency, that is a fundamental component, and then there are harmonics. Now, today we have demonstrated that if we decrease, so at 2.5 kilohertz the current loop is perfectly stable. Now, we are reducing that to 2.25. So, let us go to 2.25. So, we are slowly decreasing the input voltage, and we are coming at 2.25, and this 2.25, it is almost kind of verge of instability. That means, you can see if we just stop it, you can see that it is almost instability is just about to start. There are actually sub-harmonic is just starting to create. They are not exactly matching, some cycle they are matching, in between there is a slow instability. So, now we are actually running, and we are coming to 2.2 volt. When we go to 2.2 volt, which you have shown, you can clearly see that there is sub-harmonic instability, and this spectral peak is coming, that is a sub-harmonic which is at 100 kilohertz, that is clearly coming, and this we have shown in today's class. And then what we are going to do, we are going to now reduce this voltage to 2 volt. If we take it to 2 volt, now you will see that 2 volt, we have seen that this instability is coming, which is almost coming to a situation where it becomes like 100 kilohertz, but still there are some switch on and off, and the spectral peaks is now very sharp at 100 kilohertz. Sub-harmonic is very dominant, and you can see that ripple has drastically, peak to peak has increased, so it will affect the RMS current. Now if we further go to 1.9 that you have shown, if we go to 1.9 in volt, then it looks like the switching frequency become half. There is no component here, so fundamental is coming at 100 kilohertz, then all the harmonic. But actually it is not 100 kilohertz, it is set to 200 kilohertz because it is a nonlinear phenomena that is making like 100 kilohertz. So now we are going to start the ramp compensation, and we have shown at this 1.9 volt there is a provision of the switch, and this switch we are giving from externally. If we consider this switch, now we have added a ramp, but it is a very slow ramp. So if we add this ramp, you see the nature of instability got changed. That means in between something happening, but it is actually not stable, but there is some improvement in the stability compared to the earlier case when it was totally looking like 100 kilohertz. Now we are going to 2 volt operation. So 2 volt, it is also unstable, but it is somewhat better than the earlier case when there was no ramp compensation. Now we are further increasing the input voltage, so we are going to 2.2 volt. We want to show 2.2 volt. So 2.2 volt now it is stable, which was unstable earlier. Now with ramp actually it is stable, and if we further increase to 2.5, then it was stable both the cases. So by that way we have seen that the ramp compensation can make it stable, and when there is no ramp compensation, then it was unstable from 2.25 below 2.25, but we added ramp, it was stable, but it was not stable even at lower voltage. So we need to increase the ramp, and we have discussed that higher ramp can take the current mode control close to the voltage mode control, which is not desirable. So we have just completed our video demonstration. So we have discussed here sub-harmonic instability in mixed signal current mode control. We have shown experimental case studies. We have also considered ramp compensation for stabilization. We have shown the limitation of ramp compensation, and we have also discussed what is the impact of current loop instability in terms of RMS quantity and the power spectral density. And we will discuss some aspect quantitatively in the last week of the lecture. That's it for today. Thank you very much.